Ready, na? Okay. Yes, good evening and welcome back once again. Sorry, I'm 20 minutes behind schedule, like yesterday. Uh, I almost completed the convection heat transfer. I have covered almost every aspect related to convection heat transfer. There weren't many doubts. Someone asked me now yesterday to explain the problems and pins. Maybe we have gone a little further. We have almost completed convection heat transfer. Now, one boy asked me, sir, do we need to remember all these formula regarding flow, spheres, and tube, bank of tubes? It's not really possible there. And I just don't take it very serious. You cannot by heart so many equations. They are not very common also. Even in case, if they ask you a problem on flow over a cylinder and a sphere or bank of tubes, they should provide you with the appropriate correlation for convection heat transfer. Without that, you cannot actually solve it. You are not expected. In a nutshell, what I say, you are not expected to, remember all this. And what is the difference between drag force and lift force? I thought I have sufficiently explained with the diagrams and a few examples also. See, if an aeroplane is flying, it's because of when it is initially taking off, it is because of the lift force. What is it? Lift force is against the gravitational pull. Now, how is this lift force coming into picture? It is because of the pressure differential. Now, let me say I created low pressure on top of the body and high pressure at the bottom of the body, then quite obviously pressure differential causes the body to move vertically. A force helps it to vertically move. That is the lift force. A drag force with skin friction and shear stress, I've explained, whenever a body is moving, you have, when fluid is flowing against it, you have the entire surface of the body offering, frictional resistance. And this frictional resistance opposes the forward motion of it. And that is the reason why people talk about aerofoil designs, aerofoil sections, aerofoil frontal area. That means what? When you are traveling at some speed, let the frontal area of the vehicle, when I'm talking about a vehicle, not offer too much of a resistance for air and therefore dispel the air, meaning the frictional forces will be minimum. So drag force is something like, I said, the swinging of a cricket ball. One side you make it rough, one side you make it smooth. When you deliver it in a way, on smooth side, the resistance is less and the friction is less, and therefore ball can travel a longer distance. On a rough side, the resistance is more. This arm of the ball is reluctant to travel the equal distance, and therefore a cut to the path is being taken by the ball. So basically, when it is the forward resistance offered for the forward motion due to the friction of the fluid particles is fine. And lift is something is created by the design such that pressure differential causes the force resultant acting upwards so that it is lifted. In an aeroplane, you need to design it in such a way that the upper pressure is lower and at the bottom of the aeroplane the pressure is high when it is moving with certain speed, so that higher pressure pushes it up. Whereas the same when you talk about an automobile on a road, the automobile on a road shall have low lift force. You don't want it to be taken off from the road. So you always design it otherwise. the lift force should be, in the reverse direction, so that, vehicle always is kept intact on the road. So the stability of the vehicle will be more. So with that, I think I have explained the convection, lift and drag force. And someone asked me, what is the explain the natural convection over surfaces. Maybe this also I've taken enough time to explain. Natural convection on a horizontal surface, vertical surface should not be a problem. If this is your vertical surface, if the surface is heated and cold air is there, the colder air, when air coming in contact with the hot surface, get heated up, they vertically move. And while moving up, I said the first layer of particles which are sticking onto the surface, they sit pretty on the surface, and therefore the frictional forces will not allow it to move vertically upwards. But whereas the remaining layers, as you move away from the plate, these layers will go. And again, when you move considerable distance, the temperature difference will not be felt here, and therefore buoyancy forces are not there. So if you find a velocity profile like this, velocity is zero at the surface, slowly it increases, reaches a maximum, and thereafter it falls, and a boundary layer is formed. If it is a colder surface, and hot air is coming in contact with it, now the hot air will come in contact with it, it becomes cooler because it loses heat, and therefore become heavier. It wanted to move down. It moves down. Heavier particles always moves down in the medium. So therefore, these heavier molecules, whenever they come, lose their heat, and temperature density is increasing, and therefore they move down. So a boundary layer is formed from top to bottom. I have drawn both these figures. Okay, very quickly. I don't know what confused you. What is this? This is for hot plate in a colder environment, colder fluid. TW is less than T infinity. These are the two cases. And this is not very difficult for you. The velocity profiles and temperature profiles I have drawn. In this case, it will go down, and therefore it will be like this. When this is not very difficult for you to digest or understand. Whereas horizontal surface, I said, when you talk about horizontal surface, there may be a favorable condition, there may be an unfavorable condition. What is a favorable condition? If it is a hot surface, horizontal, on top of it, air is coming in contact, it gets heated, heated molecules can vertically go up, buoyancy effects, and therefore this is highly conducive. Any molecule that is coming here to the plate gives away picks the heat from the plate, and its density reduces, go up. So absolutely no resistance for the particular movement, and always a colder particle can come here, acquire the heat, and go on. Heated, go on. So this is convenient. When it is a colder surface, air is at 80 degrees centigrade, plate is at 40 degrees centigrade. 80 degrees centigrade air comes here, it becomes cooler because heat transfer takes place within them, and it becomes 40. So in an environment of 80 degrees centigrade air molecules, a 40 degrees centigrade air molecule is heavier because it lost its temperature, and therefore it tries to settle down on the plate. So all those molecules which are coming near the plate, they become heavier, they sit pretty on the plate. And therefore, after some time, a fresh hot molecule cannot come in contact with the plate. It can only interact with the other fluid molecules, but it can never interact with the plate because already a few layers have been deposited on the plate because of the heaviness of the molecule. So this is unfavorable. A similar such condition I have explained at the bottom surface also. If the bottom surface cooled, any molecule coming here, losing heat, becoming heavier, they can easily go down. There is no restriction. Whereas, cold air coming in contact with the hot particles, they come, they get heated up, they wanted to go up, plate is obstructing it, all molecules settle down here, and fresh molecules will not come. So that's how natural convection, I think I've explained in vertical case, in the horizontal case, I have given you all the equations. So, without taking further time, I think other than that, there are many. The equations I have summarized, the continuity equation, the first one, and the second, third, fourth are different forms of, Navier-Stokes equation or momentum equation. The fifth equation is the energy equation. This you can get it from any textbook. I just wanted to give you these equations. Now, the force of convection category wise, let me very quickly run through. For laminar flows over a flat plate, for all flat plates, the critical Reynolds number is 5 into 10 power 5. And Nusselt's number is equal to this, Nusselt's X. X means local value. And this is for a constant wall temperature, means entire plate should be at a constant temperature. So this is the equation. And average heat transfer coefficient, I have told you for all laminar flows, it is local value multiplied by 2. Not only for H, it is applicable for CFX also. CFX also, if you multiply it with 2, you get the average value. And hydrodynamic boundary layer, the Blachius solution, 5x divided by Re power 0.5, and the exact 1 carbon exact solution is 4.9 something divided by Rx. Most of the data books carry this value of hydrodynamic boundary layer thickness, 5x divided by square root of Rex. And thermal boundary layer is relation between thermal boundary layer and hydrodynamic boundary layer is dt divided by dh is equal to 1 by Prandtl number power 1 by 3. This is the equation. Okay. So, and the skin friction coefficient also I told you. The local value is given by 0.664 divided by under square root Re, Reynolds number. And average value is twice that of that. 0.664, if you multiply that with 2, you get this. Whereas if the wall is at a constant heat flux condition, meaning the plate is at a constant heat flux. In any of these convection cases, you come across these two conditions. What do you mean by constant wall temperature and constant heat flux? If your surface is this, if the entire surface for the entire heat transfer is maintained at a constant temperature, say everywhere on the surface it is 80 degrees centigrade now and whenever you measure, it is 80 degrees centigrade constantly maintained, then it's a constant wall temperature. What do you mean by constant heat flux? Someone said, due to this convection, 500 watts per meter square of heat is steadily leaving this surface. Or he may further say, there is an electrical heater at the bottom of the plate which is releasing 500 watts per meter square of heat. And without any further losses, the same heat is conducted through the solid and convected. That means what? This plate is either receiving or transferring or throwing out a certain quantity of heat per unit area. Constant quantity of heat per unit area. So if it is 3 meters square of surface area, every meter square releases say 500 watts of heat. So that is a constant heat flux. There you don't know what is the temperature of the solid, but you know what is the the heat releases from the surface. Now in this case, calculating constant heat flux, calculating TFS. What is film temperature? Film temperature is the average temperature of plate and the ambient fluid temperature. So you can make an assumption that since wall temperature is not available, fluid properties are taken at a film temperature, fluid temperature state. Okay, so a constant wall temperature, constant heat flux conditions. Okay. For a turbulent flow, fully turbulent from the leading edge. I told you, when this case arises, when a fluid is flowing over a flat plate like this, it will be laminar for some distance and thereafter it is turbulent. It is laminar for some distance and thereafter it is turbulent. If the laminar length is small as compared to length of turbulent flow, I can ignore this and assume that it's fully turbulent. So no such flow will be fully turbulent right from the beginning, but here the case is I am ignoring the smaller length of the laminar. and therefore it is treated as fully doubled. Or else I have a turbulent generator right at the beginning. So as the fluid is entering onto the plate itself, I use these turbulent generators, randomize the motion, and therefore I treat them as fully turbulent also. So in this case, local Nusselt's number is given by this equation, and average Nusselt's number is given by this equation. And the relation for turbulent flow is 1.25 times. Whereas in laminar flow, local and average, it is the average is twice that of local, whereas here average value was 1.25 times that of local heat transfer coefficient. Okay, so in a turbulent flow for a constant heat flux condition, okay, Nusselt's number of constant heat flux case is 1.04 times of Nusselt's number of a constant wall temperature, meaning this equation into 1.04. This equation into 1.04. So flow across cylinders, this is the generalized equation, cylinders and spheres. Nu is equal to CR Reynolds power M Prandtl number power 1 by 3. This is a very generalized equation that we use for cylinders, and C and M value depend on the Reynolds number. C and M value depends on the Reynolds number. And again, I said you cannot remember so many details. Maybe you look for such details in the problem itself. If it is in a gate or IES case, you need not by heart these values. Okay. For a flow across spheres, meaning over the top of the sphere, so this is the case. Nusselt's number is equal to 0.37, Reynolds power 0.6. And for internal flows, when a fluid is flowing through the pipes, I told you characteristic dimension is 4 into area of cross section divided by wetted perimeter. And again, in these two cases are there, one constant wall temperature, constant heat flux, and when it is laminar flow, I mean fluid is flowing laminarly inside a tube, Nusselt's number is equal to 3.66, and so simple for you to remember, not in terms of Reynolds number and Prandtl number. Straight away Nusselt's number takes a constant value, 3.66 for constant wall temperature, 4.36 for a case of constant heat flux. And there comes a very popular equation. Most of the fluid flows through tubes. They are all turbulent in nature, most of the fluid flows, even for the smallest velocities of the fluid flow. And they are turbulent in nature. And I told you certain times, they don't give velocity, they give mass flow rate. When they give you mass flow rate, velocity can be calculated by using continuity equation. Mass flow rate is equal to rho AV, density area of cross section multiplied by velocity. And once you know density area of cross section and velocity can be calculated with mass flow rate, then that velocity can be used in Reynolds. So this is a very popular equation. Nusselt's number is equal to 0.023 Re power 0.8 Prandtl number power 1 by 3. And this is called Dittus-Boelter's equation. Dittus-Boelter's equation. And N, the power of Prandtl number N will be 0.3 for cooling and 0.4 for heating. Okay. And natural convection, I said vertical surfaces, you have this equation, Nu is equal to 0.59 into GRPR whole raised to the power 0.25. And GRPR, once again, I just remind you, my dear friends, GRPR is called Rayleigh number also. The product of Grashof and Prandtl is Rayleigh number. And Rayleigh number decides whether the flow is laminar or turbulent in case of natural convection. And for turbulent flow over vertical plates, this equation is called McAdams equation. And 0.10 GRPR whole raised to the power 1 by 3. So this is a local value. Average value is this 4 by 3 of Nusselt's local. So this you can use. And for a horizontal plate, upper surface heated, Nusselt's number is equal to 0.54 GRPR whole raised to the power 0.25. Okay. And for a horizontal plate, lower surface heated. See, upper surface heated is always a favorable condition. Lower surface heated is always unfavorable condition. Reverse is also true. Okay. So heat transfer coefficient is given this way. One is favorable, one is unfavorable. Inclined surfaces, I have told you, wherever G is there, you substitute G cos theta. There ends the problem. Okay. But the angle is with the vertical. Very quickly, can we go through some of the problems? Very quickly, just to make you comfortable solving the convection heat transfer problems. The convection heat transfer coefficient between a surface at 100 degrees centigrade and ambient air at 30 degrees centigrade is 50 watts per meter square degree centigrade. Okay. Calculate the heat flux leaving the surface by convection. See, it's child's play. Q is equal to HA delta T. Delta T is given. H is given. He is asking, he has not given area, whereas he is asking you to calculate heat flux. So, small q is equal to H delta T. Straight away you can. Straight away, Q by A, heat flux, is H into delta T. Don't worry about all those diagrams and all, it's a simple equation. Now, air at 30 degrees centigrade is flowing over a flat plate of size 0.5 by 0.2 meters. If the convection heat transfer coefficient is 150 watts, determine the heat transfer rate from the air to one side of the plate when the plate is maintained at 130 degrees centigrade. See, you may ask, when a plate is given, the plate may be, even heat transfer may be taking place on either side of the plate or one side of the plate. So you must be fully aware whether it is on either side or one side of the plate. He has made it very clear. If heat transfer is taking place on either side of the plate, like it's taking place here as well as here, so it is double the heat transfer, right? So one side of the plate, and again it's not a big deal. Q is equal to HA delta T. A flat plate having surface area 8 meter square is hanging freely in air. So a flat plate is hanging in air. Okay, the temperature of the surroundings is 30 degrees centigrade. Solar radiation is falling on one side of the plate at the rate of 3 kilowatt per meter square. What should be the convection heat transfer coefficient? W in meter square coefficient in watts per meter square degree centigrade. Of course, that is the unit of heat transfer coefficient. If the temperature of the plate is to remain constant at 45 degrees centigrade. So, surrounding temperature is 30 degrees centigrade, plate temperature is 45 degrees centigrade, plate area is 8 meter square, it is horizontal, right? And what is happening? It's a horizontal. On top of it, solar radiation is falling, sun is throwing radiation onto it, and how much is falling? 3 kilowatts per meter square. What is the total heat falling because of solar radiation? 24. 8 3 is 24. This and this. This, oops, and this. So, 24 kilowatts of heat is falling on this plate. Now, if you assume no other laws, all the solar radiation falling on the plate should be convected on the other end. So therefore, you calculate, okay, so A gets cancelled, and of course, even if you want to use A, placed horizontal in an ambient air at 32 degrees centigrade is losing heat. If Nusselt's number is 50 and thermal conductivity of air is 0.5 watt per meter Kelvin, find the heat transfer coefficient. Nusselt's number is given 50, and it's not said it is natural, what kind of a condition it is, but assuming that it's placed in air, ambient air is always treated as natural convection condition. So for a horizontal steam pipe placed in ambient condition, what is the characteristic dimension? For all horizontal cylinders, the characteristic dimension in natural convection is its diameter. Is it diameter? Please remember, I have told this yesterday. So it is diameter is the characteristic dimension. Nusselt's number value was given, and what is Nusselt's number? Nusselt's number is equal to HL by K. You are asked to find H. K is given. K is given. And if you know the characteristic dimension, Nusselt's number is equal to HL by K, and since D is the characteristic dimension, you can calculate. D is given here, 10 centimeters diameter. This is an unwanted detail. We don't use that in calculating the problem. In Nusselt's number is equal to HD by K, and therefore calculate H. Determine the thermal boundary layer thickness. If the hydrodynamic boundary layer thickness over a flat plate surface is 0.2 mm, delta H is equal to 0.2 mm. Take the dynamic viscosity mu as 3.5 into 10 power minus 6 Pascal second. Specificity is given and thermal conductivity is given. So mu is given, Cp is given, thermal conductivity is given. Do you remember any dimensionless number? Quite obviously, you remember Prandtl number. What is Prandtl number? Mu Cp by K. Mu is given and Cp is given, specificity is given, and thermal conductivity is given. Mu Cp by K, the Prandtl number can be calculated. What is the relationship between the hydrodynamic boundary layer and thermal boundary layer? Only in terms of Prandtl number. Only in terms of Prandtl number. I have just told you that relation. Delta T by delta H is equal to, okay, 1 by Prandtl number power 1 by 3. So this is a relation. Just now I have shown it to you. Don't remember that? Here it is. Here it is. Delta T is equal to delta H into Prandtl number power 1 by 3. Minus 1 by 3. Okay. So you are given delta H. You are given parameters to calculate Prandtl number. Hydrodynamic boundary layer thickness can be calculated. Okay. Now, air flows over a heated plate at a velocity of 100 meters per second. The local skin friction coefficient at a point on the plate is CFX. Skin friction coefficient is CFX. Is 0.008. It's a coefficient, no units. Estimate the local heat transfer coefficient at this point. Estimate the local heat transfer coefficient at this point. Now you need to use the Colburn analogy. Stanton number is equal to H divided by rho CPV, and from this you calculate heat transfer coefficient. Is it okay? Please go through it. Prandtl number can be calculated because all these three parameters are given. Stanton number is equal to H divided by rho CPV, and Prandtl number already you have calculated is equal to CF by 2, and therefore you calculate. A fluid of thermal conductivity 1 per meter Kelvin K of the fluid is any Reynolds number less than 2300 indicate a laminar flow. So it is a laminar flow, and pipe diameter of 10 centimeters is given. Thermal conductivity is given. Determine the heat transfer coefficient of uniform heat flux and uniform wall temperature conditions. What is it? Just now I said for all laminar flows through the pipe, Nu is equal to 3.66 per constant heat flux and Nu is equal to 4.36 per constant wall temperature. Both are standard values, right? So laminar flow, instead of constant heat flux is 4.36, you calculate H is equal to Nu is equal to HD by K. Because fluid flow through a horizontal tube, the characteristic dimension is the diameter, 4 AC by wetted perimeter. So characteristic dimension is diameter, Nusselt's number, these equations I have already given for constant heat flux and constant wall temperature. And nu is equal to HL by K. Here characteristic dimension is D. K value is given in the problem itself. And diameter is given in the problem. And this value you calculate heat transfer. Water is passed through an annulus formed by two tubes of 5 centimeters and 3 centimeters in diameter at a velocity of 0.5 meters per second. Velocity is given 0.5 meters for the water and it is flowing through an annular space. What do you mean by that? There are two concentric cylinders, pipes, and the water is flowing in the gap between them, in the annular space between them. Okay. If the inlet temperature of water is 20 degrees centigrade and 3 centimeter diameter tube temperature, diameter of the tube is 3 centimeters, it is maintained at 80 degrees centigrade constant wall temperature. Find the heat transfer coefficient between water and small tube surface. Water and small tube surface. Okay. So, I said, what is the characteristic dimension in case of annular space? Again, you use 4AC by wetted perimeter, and yesterday itself I have told you that it is a fluid is flowing here. Fluid is flowing here. It's a small d and it's a capital D. So 4 into pi by 4. The area for the fluid passage is the gap between them, gap in the cross section area, divided by wetted perimeter, right? Pi into d plus d. So effectively, this is d minus d. Capital D minus small d. So this is the characteristic dimension that is used. Reynolds number is equal to rho V L by mu or V L by nu. Nu is kinematic viscosity. So here in the problem, the kinematic viscosity is given, absolute viscosity is not given. Even if you want to calculate absolute viscosity, you can multiply that kinematic viscosity with rho, you get absolute viscosity. Now you calculate Reynolds number. You calculated Reynolds number to be 18.2 into 10 power 3, and therefore it is greater than 2300. Flow is turbulent. Flow is turbulent. So you can also calculate Prandtl number from the given parameters. Prandtl number you are getting is 3.64. So the flow is turbulent. Fluid is flowing through a pipe. For turbulent fluid flow, you use the popular Dittus-Boelter's equation. Now, fluid is entering at a temperature less than the plate temperature. So, therefore, fluid should be heating, and therefore, please make a correction here. It should be 0.5 for heating, not 0.3. It can take either 0.3 or 0.4. So, you should use 0.4 here. I'm sorry for this. So now you calculate Nusselt's number. Nu is equal to HL by K, where characteristic dimension is D minus D, and therefore you calculate what is heat transfer coefficient. In a laminar natural convection, a vertical wall is maintained at 150 degrees centigrade. A vertical wall is maintained at 150 degrees centigrade, having average Nusselt's number 45. Nu is 45. Vertical plate temperature is 150. With surrounding air at 30, T infinity is 30, plate is at 150. If the wall temperature becomes 45, all parameters remaining same, what would be the average Nusselt's number? Okay, so wall temperature 150 ఉన్నప్పుడు Nusselt's number is 45. Surrounding fluid temperature 30, అది మారట్లేదు. Then wall temperature 150 కాకుండా 45 ఉంటే ఏంటి Nusselt's number అన్నాడు. ఓకే, లామినార్ ఫ్లో లో natural convection equation లో మనం Nusselts is equal to RA power 1/4 వేసుకొని, ఓకే, Nusselts number is directly proportional to Grashof number power 4. ఎలా ఇప్పుడు ఇక్కడ కూడా ప్రపోర్షన్ తీసుకోవాలి. Nusselts number is proportional to Rayleigh number power 1/4 for laminar flow. అంటే Nusselts number is equal to C into Rayleigh number power 1/4 అనుకోండి. C is a constant. So Nusselts number is proportional to Grashof power 1/4. What is Grashof number? Grashof number is G beta delta T L cube divided by nu square. Temperature change ki, okay, temperature change ki Grashof number is directly proportional. One minute please. ఇది చూడండి, ఈ ఈక్వేషన్ చూడండి. What did he say? Laminar flow kada, natural convection kada. What is the equation for vertical surface laminar flow? Nu is equal to 0.59 GRPR whole raised to power 0.25. 0.25 ante 1/4 kada, isn't it? So Nu is equal to 0.59. GRPR ఏమన్నాను నేను? ర్యాలీ నెంబర్ అన్నాను. ర్యాలీ నెంబర్ పవర్ 1/4, 0.25 or 1/4. That means what? Nusselts number is directly proportional to Rayleigh number power 1/4. What is Rayleigh? Rayleigh is product of GRPR, and therefore Nusselts number is also directly proportional to GR power 1/4. What is this Grashof number? Grashof number is G beta delta T L cubed divided by nu square. Can you imagine this? Right? So GR is directly proportional to delta T. Ikkada GR is directly proportional to delta T. Otherwise, so Nusselts number is directly proportional to delta T. Nusselts number is directly proportional. That is the logic I have taken. Okay. Now, Nusselts number is directly proportional to delta T power 1/4. Delta T ikkada GR power 1/4 kada. GR is directly proportional to delta T kabatti it is delta T power 1/4. I'm sorry for this. So delta T1 divided by delta T2 whole power 1/4 is equal to Nu1 by Nu2. Nu1 ఇచ్చేసాడు. ఓకే, Nu2 ఎంతో చెప్పంటాడు. అంటే Nu1 ఎంత ఉంది? 150 degrees ఉన్నప్పుడు T1 is T1 అంటే T1 is 150, T plate is 30 degrees, T fluid is 30 degrees centigrade. What is delta T? Wall temperature, fluid temperature మధ్య difference ఎంత? 120 degrees centigrade. So delta T1 when it is 120 degrees centigrade, Nu1 is 45. When temperature difference is 120, Nusselts number is 45. Now, what is the temperature of the wall? 45. And what is the temperature difference between wall and fluid? 45 minus 30, 15. So, Nusselts number is directly proportional to delta T power 1/4. You know delta T1 earlier, first case. You know Nusselts number in the first case. You know delta T in second case. You wanted to find Nusselts number in the second case. So now I think anyone can do this problem. So delta T1 by delta T2 whole raised to power 1/4 is equal to Nu1 by Nu2. Nu2 is what you wanted. So therefore, you can. Nu2 is equal to Nu1 divided by delta T1 by delta T2 whole raised to power 1/4. So Nusselt's number is this. Air at 35 degrees centigrade flows across a cylinder of 40 diameter at a velocity of 50 meters per second. The cylinder surface is maintained 180 degrees centigrade, not through the cylinder, it is across the cylinder. Find the heat loss per unit length, properties at mean temperature. All the properties are given, and my gosh, it flows across a cylinder annadu. It should be through the cylinder, otherwise you cannot use this equation, right? So whatever he has given the relation, straight away you use this. Okay. So Reynolds number you calculate, rho VD. For all these, please remember the characteristic dimension is very, very important. Without that, you cannot calculate Reynolds number and Nusselt's number. So for each and every case, I have clearly given you what is the characteristic dimension. So for a pipe flow, D is the diameter. So rho V D by mu is the Reynolds number. You calculate Reynolds number, you find whether the flow is laminar or turbulent, but in this case, he has straight away given you the equation. Calculate Prandtl number mu Cp by K. All these properties are given, and he has given the Nusselt's number equation also to you. Straight away substitute the values there, and Nusselt's number is equal to 0.95 and Hd by K, Hl by K, where L is the characteristic dimension. So D is the diameter, that becomes the characteristic dimension, and H bar is equal to this, right? So Q is equal to, when once you calculate H, Q is equal to HA delta T. See, a fluid is flowing over a flat plate has the following properties. Dynamic viscosity mu is given, specific Cp is given, thermal conductivity 0.5 is given. Mu Cp by K is Prandtl number. Straight away you can calculate Prandtl number. Hydrodynamic boundary layer thickness is given. You are asked to calculate thermal boundary layer thickness. Delta T by delta H is equal to 1 by PR whole raised to power 1 by 3. Straightforward equation. Okay. So when you use Prandtl number mu Cp, calculate Prandtl number is equal to 1. And blindly you say, for all Prandtl numbers equal to 1, you say delta H is equal to delta. Hydrodynamic boundary layer thickness is equal to its thermal boundary. Okay. So some of these we go to another set of questions. Maybe they will be interesting to you. I'll just tell for another 20 minutes. Let me go through this quiz. Both on free and free of forced convection, let me take you through. A coolant fluid at 30 degrees centigrade flows over a heated flat plate maintained at a constant temperature of 100 degrees centigrade. A plate is maintained at 100 degrees centigrade, fluid is moving at 30 degrees centigrade. T infinity is 30, plate temperature is 100 degrees centigrade. The boundary layer temperature distribution at a given location on the plate may be approximated as within the boundary layer temperature distribution. And how the temperature is varying within the boundary layer. Okay, T is equal to, a function of Y is given. T is equal to 30 plus 70 exponential of minus Y and e power minus Y and 70 into e power minus Y, where Y is in meters. Y is the distance in meters. The Y, of course, need not be specified. When X is the fluid flow direction, Y is the direction perpendicular to it. When this is x direction, y of course is perpendicular to the plate. Right? Now there is a boundary layer on top of it. Okay. Within the boundary layer, along the y direction, temperature is given as a function of y. Temperature is given as a function of y. Okay. If the distance now, okay, T is in degrees centigrade, fine. If thermal conductivity of the fluid, K of the fluid is 1 watt per meter Kelvin, the local convective heat transfer coefficient at that location will be H and K is given at that particular location, T is known. You know, when you have a little complicated, but you need to understand very clearly. See, let me take a horizontal plate. What did I say? The first layer of molecules, they sit on the plate. They are establishing a physical contact with the plate. And under no slip conditions, I'm not expecting any relative motion between them. They are rigidly attached to the plate. Now, the heat transfer, whatever happens from the plate, I've told you already, initially happens to the fluid only by conduction heat transfer. First layer to the first layer of molecules which are deposited, since they are establishing a physical contact with the plate, the heat transfer to the first layer of molecules is only by conduction heat transfer. And the conduction heat, whatever conduction heat transfer happens at the first layer, simultaneously upward it should be convected. Now, what is the conduction heat transfer? Where is it happening? It is happening in the fluid region to the first layer of fluid, and therefore the heat transfer where at y is equal to 0. What is y? Y is the direction normal to this. Y is equal to 0. In the y is equal to 0, heat transfer at y is equal to 0 is happening because of conduction heat transfer. Are you all understanding? I said the molecules are sitting pretty on the plate, they are not moving at all, there is a physical contact established, the mode of heat transfer can be only conduction. Mode of heat transfer can be only conduction. So conduction heat transfer is given by Fourier's law of heat conduction. Q is equal to minus Ka dt by dx. Minus Ka dt by dx. Okay. Now, dt by dy. In this case, heat transfer is moving in this direction. So therefore, it is y. Where at y is equal to 0. Where dt by dy? At y is equal to 0. Because only at y is equal to 0, conduction heat transfer is happening. Remaining, it is convection heat transfer. Thereafter, the layers are moving and therefore it is convection. Now, if you can calculate dt by dy and substitute y is equal to 0 in that, you get this value of dt by dy. Okay. And that, if you know the thermal conductivity of the fluid particles, then you can calculate Q. Right. And the same Q should be equal to Q convection. Where convection from the second layer onwards, the same heat is communicated by convection heat transfer. So when you use this, I said, please listen to me carefully. Initially, it is by conduction heat transfer where on the surface where molecules are sitting. Where is that? On the surface, y is equal to 0. Heat transfer is by conduction, and Q is equal to minus K dt by dy, where at y is equal to 0. The same heat will be convected further, and therefore that's equal to Q convection. So, if you're going by that, See, given what is temperature, temperature is given as 30 plus 70 into e to the power of minus y. You find dt by dy. You find dt by dy. What is dt by dy to this? 30 70 into e to the power of minus y is e to the power of minus y into dy of minus y, that's equal to minus 1. So therefore it is minus 7. And you substitute y is equal to 0. E to the power of 0 is equal to 1. So ultimately it is minus 7. What did I do? No. If I have confused, I'm sorry. Simple, it's simple. T as a function of y is given. Get it differentiated with respect to y. And wherever after differentiation, wherever y is there, you substitute 0. That's it. So it is minus 7. Very simple. And what is heat transfer? I assume unit area, let me say. Q is equal to minus K of the fluid into dt by dy at y is equal to 0. That's equal to Q convection. Didn't I? Q convection is equal to Q conduction. ఎందుకంటే ఫస్ట్ లేయర్ లో కండక్షన్, దేర్ ఆఫ్టర్ ఇట్ ఇస్ కన్వెక్షన్. సో therefore I equate this to the already I have calculated dt by dy as minus 70. K of fluid is given as 1. Problem lo ichchadu. Thermal conductivity of the fluid is 1 watt per meter Kelvin. Okay. So therefore minus of 1 into minus 70 is 70. Q is equal to H into Ts minus T infinity. Plate temperature ichchadu, ambient temperature ichchadu. And this concept nenu first lo meeku forced convection fluid flow over a flat plate cheppinappude cheppanu. The first layer of molecules will not move, they will be under no slip condition. They establish a firm physical and thermal contact with the plate, and therefore the first layer heat transfer is by conduction heat transfer only. Heat transfer is by conduction heat transfer. Right? So therefore you calculate the properties of mercury at 300 Kelvin are density, specific heat at constant pressure. Specific heat is given, density is given, dynamic viscosity is given, and thermal conductivity is given. The Prandtl number of mercury is mu Cp by K. Simple. Prandtl number for any fluid is mu Cp by K. Mercury is also a fluid, and therefore you substitute the value of mu Cp and K to get this. No, but remember, if this problem, if you can use it, for all air it is somewhere around 0.7, 0.66 to 0.7 air. Okay, for water it is 3 point something. Prandtl number for mercury AC it is such a low value, 0.025, close to 0.025. What does it mean? When Prandtl number is low, I said, Prandtl number low, thermal boundary layer, hydrodynamic boundary layer, thermal diffusivity effects are felt longer. అంటే థర్మల్ బౌండరీ లేయర్ పైన ఉంటుంది, హైడ్రోడైనమిక్ బౌండరీ లేయర్ బాగా కింద ఉంటుంది. సో హీట్ ట్రాన్స్ఫర్ బాగా జరుగుతుంది, whereas the viscous effects will be felt only for a very short distance. The average heat transfer coefficient on a thin hot vertical plate suspended in still air can be determined from observations of a change in plate temperature with time as it goes. A plate is suspended in air, and the average heat transfer coefficient can be calculated by knowing the temperature changes. Assume the plate temperature to be uniform at any instant of time, and radiation heat exchange with surroundings is negligible. Ikkada radiation heat transfer emi jaragatledu. Radiation heat transfer ledu. Any given instant plate temperature is a constant wall temperature. Yes. The ambient temperature is 25 degrees centigrade. The plate has a total surface area of 0.1 meter square, and the plate mass is 4 kg. The specific heat of the plate material is 0.25 kilojoules. In a variety ga, if plate is suspended vertically in air, the mass is 4 kg antunnadu. The surface area is 0.1 meter square antunnadu. The specific heat is 0.25 antunnadu. The convective heat transfer coefficient in watts per meter square Kelvin at the instant when plate temperature is 225 and the change in the plate temperature with time is dt by dt. Change is dt by dt and a change in plate temperature with respect to time is 0.02 Kelvin per second. ఉన్నప్పుడు ఏం చేస్తారు? Simple అండి. This solution is so simple. See, there is a plate. There is a plate. Initially, it is at some temperature, or at an instant, it is at one temperature. Every time convection heat transfer is taking place, and when convection heat transfer is taking place, this temperature is decreased. And this plate is not maintained at a constant temperature all through this experiment. But at any instant, plate will be at a constant temperature. Okay, 225 degrees centigrade initially, some convection heat transfer is taking place. How much convection heat transfer is taking place? Q is equal to HA delta T. H is the heat transfer coefficient. That's what delta T and the temperature of the plate minus temperature of the floor. And whenever some convection heat transfer is taking place from the plate, what happens to the temperature of this plate? It decreases. If it is at 225 now, when some heat is removed by convection heat transfer, it reduces. The plate temperature change entundante per every second 0.02 Kelvin tagutadi. Per every second 0.02 Kelvin tagutadi. Ante enta heat tagutundo, enta heat plate loss ayindi atla calculate chestam. MCP delta T. Mass of the plate is given. Specific heat is given. Temperature change, if you know, initially at 225 and next second it is losing 0.02 Kelvin. So ultimately the next plate temperature is known. So MCP delta T is the heat lost by the plate and the same heat must have been removed by convection. Should be equal to HA into T minus T infinity. So simple. 4 is the mass of the plate, Cp is the specific heat of the plate, and kilojoules lo ichada. You should be very careful. If it is given in kilojoules, convert that into thousands. And simply don't use kilos in calculations, right? So 4 into 2.5 kilojoules annaruga 2.5 into 10 power 3 into dt by dt is 0.02. I mean temperature change of the plate per unit time. That's equal to HA delta T. Delta T is plate temperature is 225 and ambient temperature is 25. So you calculate what's okay. When you calculate H, it is 10. Data for next to 2 questions ki data ichcharu. Entity, solve the problem, choose the correct answers. Heat is being transferred by convection from water at 45 degrees centigrade, 48 degrees centigrade to glass plate which is at 40 degrees centigrade. Glass plate at 40 degrees centigrade, water at 48 degrees centigrade. Idantha glass plate, ikkada paina anta water. The thermal conductivity of water ichchadu, thermal conductivity of glass ichchadu, spatial water gradient of temperature in the water, at the water glass interface is dt by dv. Ante at y is equal to 0. Ante inta sentence ki ardham entante ikkada water temperature change with respect to y is 1 into 10 power actually 1 into 104 annadu. Somewhere at the bottom he has given 10 power 4 whatever. dt by dy is given here for what? Now, what is he asking? The value of temperature gradient in the gas, water key at y is equal to 0, what is dt by dy? Now, what is this? That is given 1 into 10, 104 each. That is given. What is in our gas? At y is equal. At the same interface, what is the temperature gradient of the glass? That's what he is asking. So, you just see heat conduction from the glass should be equal to heat convection from the plate, I mean, into the fluid. And since the fluid molecules are sitting on the glass plate, initial conduction, initial transfer from the glass plate to fluid is by conduction again. So therefore, you write Q is equal to heat transfer from the water, K dt by dy, minus పెడితే రెండు సైడ్లు మైనస్ పెడతాం కాబట్టి క్యాన్సిల్ అయిపోతుంది. K of water dt by dy is equal to K of glass dt by dy of glass. Okay. ఈ dt by dy of water ఇచ్చేసాడు, dt by dy of glass కనుక్కోవాలి. సో ఇక్కడ లాజిక్ ఏం పెద్దగా లేదు. ఈ ఇంటర్ఫేస్ లో గ్లాస్ నుంచి వాటర్ నుంచి ఎంత హీట్ గ్లాస్ కి వస్తుందో అంతే హీట్ వాటర్ నుంచి గ్లాస్ కి వెళ్తుంది, అంతే కదా. సో హౌ dt by dy is of water give you how much heat is conducted by water into the plate, and the same heat is gained by glass, and that is K of glass multiplied by dt by dy. It's an area, of course it's a common area, interface kada, it's a common area. So that's how you calculate. So K of water into dt by dy of water is equal to K of glass into dt by dy. K of water ఇచ్చాడు, K of glass ఇచ్చాడు, dt by dy of water ఇచ్చాడు. Only one thing for you to calculate, and irrespective, అదే చెప్పాను కదా ఇందాక, ఇది 1 into 10 power 4 ఇచ్చాడు, అక్కడేమో 104 ఇచ్చాడు. వాట్ ఎవర్ మీరు ఏదో ఒకటి అనుకుంటే మీరు వాల్యూ ఎంత ఉంటే అంత ఇక్కడ సబ్స్టిట్యూట్ చేయడం. The heat transfer coefficient H in watts per meter square Kelvin. ఇదే మనం ఇందాక కూడా చెప్పాం. At the wall surface ఎంత కండక్షన్ జరుగుతుందో అంత కన్వెక్షన్ కూడా జరుగుతుంది. So therefore, what is that? Q is equal to HTF minus TI. The same is equal to K of water into dt by dy into W. A is common same. So I will only equate చేస్తే you get 750 watts per meter square Kelvin. Can I give you 5 minutes break? I will come back. Thank you. So, unmute. So, can I go ahead? Velocity of water inside a smooth tube is doubled. Then then turbulent flow heat transfer coefficient between water and the tube will happen? Velocity of water inside the tube will be doubled. When velocity is doubled, what is going to happen to the heat transfer coefficient? Flow through a tube. What is the equation? Nusselt's number is equal to 0.023 Re power 0.8 Prandtl number power n. Okay, where is velocity coming into picture in the calculation of Reynolds number? What is Reynolds number? Rho Vd by mu. And velocity is doubled. What happens to Reynolds number? Reynolds number will also be doubled. Remaining things being same, remaining parameters being same, the velocity, if it is increased, earlier it was V, now it is 2V, and therefore Reynolds number becomes double. Between Nusselt's number and Reynolds number, Nusselt's number is directly proportional to Re power 0.8. Okay, so Nusselt's, what is Nusselt's number? Nusselt's number is equal to HL by K. So Nusselt's number is directly proportional to H. Nusselt's number is directly proportional to Reynolds number power 0.8. So therefore, H is directly proportional to velocity power 0.8. Simple logic. Is equal to H1 by H2, H2 by H1 or Q1 by Q2 is equal to V2 by V1. That's equal to, V2 was double than V1. So it is 2 power 0.8, 1.75 or 74 times heat transfer coefficient increases or heat transfer also increases. Am I clear? Straight away, he said, velocity of water is inside a smooth tube. It is doubled when in turbulent flow condition, it is doubled. Turbulent flow equation is Nu is equal to 0.023 Re power n. So velocity, when it is changed, only parameter that changes in the equation is Reynolds. So what is the relation between velocity and Reynolds number? Straight directly proportional. When velocity increases, Reynolds number is doubled. So that means what? Nusselt's number is directly proportional to Re. Re power 0.8 or velocity power 0.8. And what is Nusselt's number? HL by K. Nu is equal to HL by K. Problem is solved. A sphere, tube, circular plate, all made of same material and having same mass, are initially heated, same mass and same density. Same material and same density, same mass. That means what? Mass is equal to density into volume. And when density is same, mass is same, volume shall also be the same. What are the three things? One is a cylinder, circular cylinder. One is a sphere. One is a sphere. Now, when you compare which one has a higher surface area, cube will have least surface area and sphere will have highest surface area for the same volume. From the same volume. Now, it's just, analyzing the regular objects. That's it, as simple as this. So, when that being the case, initially it is heated to 250 degrees centigrade, all three of them, and left at a room temperature for cooling. Is correct. It's all about which one is getting cooled first. What is heat transfer rate? Heat transfer rate Q is equal to heat transfer rate Q is equal to HA delta T. When remaining things same, material is same, fluid is same, H is same. H is same. So Q is equal to HA delta T. In all these three cases, Q is equal to HA delta T. దేనికైతే ఎక్కువ ఏరియా, so cube will be cooled faster because cube has a higher surface area for the same volume as compared to a cylinder or a circular plate or a cube. Among the three, the sphere will have lowest surface area. Among the three, sphere will have the lowest surface area. So therefore, cube will be cooled faster. Cube has higher, because cube has 6 faces. So cube will be cooled faster and then circular plate, but sphere will have the lowest. A thin flat plate, 2 meters by 2 meters, is hanging freely in air. The temperature of the surrounding is 25 degrees centigrade. I think this problem we have already solved. Air at 20 degrees centigrade blows over a hot plate of 50 by 60 centimeter made of carbon steel maintained at 220 degrees centigrade. The convective heat transfer coefficient is 25 watts per meter square Kelvin. What will be the heat loss from the plate? Okay. Plate temperature is 220 degrees centigrade. Air is at 20 degrees centigrade. Plate size is given 50 by 60 and area is known, heat transfer coefficient is known. This carbon steel, I don't know whether it is carbon steel or something else, but the data given, it is HA delta. It is straight away the equation solution. For calculation of heat transfer by natural convection from a horizontal cylinder, what is the characteristic length in Grashof number? Grashof number is G beta delta T L cube divided by nu square, where L is the characteristic dimension. So in natural convection, for a horizontal cylinder, I have always maintained diameter of the cylinder, diameter of the cylinder. And of course, here I just gave you the characteristic dimension. This is Grashof number equation. For horizontal plate, I said it is area by surface area by perimeter. Horizontal cylinder, outside diameter characteristic dimension. For a vertical cylinder or a vertical plate, it is the vertical height. For the similar conditions, the values of convection heat transfer coefficients in forced convection than in free convection. Through the diagrams I have maintained, if you are not in my earlier lectures, I can even show you that. Here it is. For all, right? I said for all natural and forced convections, natural convection will have lesser because it is the fluid motion is only because of the buoyancy effects. So the first condition is right. For similar conditions, the values of convective heat transfer coefficients are more in forced convection than free convection. Yes, it's perfectly right. In case of forced convection systems, the movement of fluid is by means of external agency. That's also right. That's also right. So since it is an external agency, you are blowing the air or directing the fluid molecule, and therefore heat transfer coefficients are very high, heat transfer rates are very high, and therefore you have yes, A and R individually true, or is the correct explanation of A. A slab of finite thickness heated on one side and held horizontal will lose more heat per unit time to the cooler air if the hot surface faces upwards when compared to with the case where hot surface faces downwards. Times I've explained. A slab of finite thickness heated on one side and held will lose more heat per unit time to the cooler air. Air is cooler, plate is hotter. If the hard surface faces upwards, if this is the hard surface, not this, not the bottom one, but the top one is the hard surface, and when it is the hard surface, when cool air comes here, it very quickly gains the heat and loses the density, vertically moves. So it's a very free way of convecting. Every time a cooler particle readily can come here, gain the heat and move away. No restriction whatsoever. Whereas if you keep it downwards and if this is the hard surface, all particles which are coming here are heated with the plate and they are sticking onto the plate. They are sticking onto the plate. And therefore, they are not giving way for the new molecule to come in contact, because these molecules, by virtue of its lower density, they always hang here and they don't have a way to vertically move because plate is obstructing. So all heated molecules accumulate here, and therefore statement 1 is correct. When hot surfaces face upwards, convection takes place easily, whereas when the hot surface faces downwards, convection heat transfer to happen, colder molecule cannot come there. So therefore, both are correct. For a flow and heat transfer, flow and heat transfer in a uniformly heated long cylindrical tube, if the flow velocity is doubled and the tube diameter is halved, there are two things happening. In a fully developed flow, flow velocity is doubled, d is d by 2 now, v is 2 into v. Then what will happen? What will d is the characteristic dimension for a tube flow. So Reynolds number is rho v d by mu. Here v is doubled, d is half, and therefore Reynolds number is not changing. Therefore Reynolds number is not changing. When Reynolds number is not changing, no, the characteristic of the fluid is not changed. Therefore Prandtl number remains same. If you say nu is equal for a tube flow, nu is equal to 0.023 Re power 0.8 Prandtl number power n. Prandtl number is not changing. Reynolds number is not changing. Therefore nu will not change. Here two things are changed. Velocity is doubled. Diameter is halved. V is 2V now, D is D by 2, 2 gets cancelled, no effect, null effect. So therefore Reynolds number is not changing, and therefore Nusselt's number will not change. But what is Nusselt's number? Nusselt's number is equal to HL by K. What is L characteristic dimension? What is characteristic dimension here? It is diameter, tube diameter. What is diameter? It is D by 2 now. It is d by 2 now. So therefore, I don't know. I'm explaining everything in air and you may not be appreciating. Say nu is equal to 0.023 Re power 0.8 Prandtl number power n. Right? Re is rho vd by mu. So velocity is in the first case it is this, and in the second case Re is equal to Re1, Re1, this is Re2. Re2 is equal to rho into velocity is doubled, a diameter is halved, divided by mu. Mu is a property, rho is a property, they are not changing. Property of the fluid is not changing. Only physical parameters are changing. So it is again rho vd by mu. So therefore Re1 is equal to Re2. Agreed? Now, Re is not changing, Prandtl number is mu Cp by K, the properties are not changing, mu Cp by K, properties are not changing, therefore Prandtl is not changing. So therefore, Nu1 is equal to Nu2. Same, it is not changing. Nusselt's number is not changing. What is Nusselt's number? It is equal to HL by K. where L is equal to diameter. So therefore, Nu2 is equal to HT by 2 now. Diameter is halved divided by K. Okay, that's equal to Nu1. So okay, so Nu1 is HT by K. So it is twice that of earlier Nusselt's number. It is twice that of earlier Nusselt's number, and therefore double of the original value. The heat transfer coefficient will be double of the original value. The Nusselt's number is related to Reynolds number in laminar and turbulent flows respectively. Okay. ఇక్కడ flat plate, laminar and turbulent flows respectively. He did not mention whether it is tube flow or flat plate. So maybe you need to go through the correlations. And normally it is Reynolds raised to the power 0.8, and therefore you can choose B. In respect of free convection over a vertical flat plate, the Nusselt's number varies with the Grashof number as. In respect of free convection over a vertical flat plate, the Nusselt's number varies with the Grashof number as, and then Nusselt's number is equal to 0.59 GRPR whole raised to the power 1 by 4. That is the equation, and therefore you need to know both the correlations. Maybe you want me to show the correlations? I will show the correlations. The question is on Nusselt's number varies with Grashof number. How Nusselt's number is varying with Grashof number? So natural convection for laminar flows, Nusselt's equal to 0.59 GRPR whole raised to the power 1 by 4, and for turbulent flows, Nusselt's equal to 0.10 GRPR whole raised to the power 1 by 3. 1 by 3. So in this case, it is GR power 1 by 4 for laminar flow. In this case, it is GR power 1 by 3. GR power 1 by 4 and GR power 1 by 3 for laminar and turbulent flows respectively. Agreed. Heat loss from a 100-meter diameter steam pipe placed horizontally in an ambient air at 30 degrees centigrade. If the Nusselt's number is 25, thermal conductivity of air is 0.03, then the heat transfer coefficient will be, okay, H T by K. So you can straight away calculate. Now, this is something very interesting. It's just a very quick recap of the numbers we have calculated, matching them. Grashof number, where it comes in free convection. Stanton number, where it comes, I said it is the ratio of Nusselt's and Peclet number. This comes in forced convection. Sherwood number is one which we are not going to discuss because we are not studying mass transfer. So Sherwood number is a number that comes in mass transfer. Just let us not discuss it now. Now, where is the Fourier number coming? Fourier number and Biot number, both of them we have discussed in unsteady state heat convection. So when you could match Grashof number to free convection, Stanton number to forced convection, Fourier to unsteady, the remaining Sherwood number automatically matches the mass. Now again matching forced convection. What do you use? Reynolds and Prandtl number you use forced convection. Natural convection, Prandtl number and Grashof number you use. GRPR. Combined free and forced convection, of course all the three numbers will be used. Grashof, Reynolds and Prandtl number. Unsteady state heat conduction with convection at the surface, Fourier and Biot number. So again the same, I believe. I think too many questions came in there. Which one of the following non-dimensional number is used to determine transition from laminar to turbulent flow in free convection? Please don't get worried. No, don't get confused. See, the transition from laminar to turbulent in forced convection, it is Reynolds number. I think we said 5 into 10 power 5 for a flat plate, 2300 for a pipe flow. We said for Reynolds number. And in natural convection, it is the Rayleigh number that decides whether the flow is laminar or turbulent. I told you specifically, for all Rayleigh number values less than 10 power 9, we find the flow to be laminar. For all Rayleigh numbers greater than 10 power 9, flow to be turbulent. Okay? So Rayleigh number is the correct answer. Again, the matching. In free convection, heat transfer transition, okay, again, it's Grashof and Pronto. Rayleigh number, it's not given as Rayleigh number. What is Rayleigh number? Rayleigh number is a product of Grashof and Pronto. That's how you get D. Nusselt's number for a fully developed turbulent flow in a pipe is given by Nu is equal to C Re power A and Prandtl number power B. The values are the standard Dittus-Boelter equation. What is it? It is Nusselt's number is equal to 0.023 Re power 0.8 Prandtl number power N. N is equal to 0.4 for heating and 0.3 for cooling. Where is it? A is equal to 0.8, B is equal to 0.4, and this. C should be correct answer. For natural convection flow over a vertical plate as shown in the given figure, the governing differential equation for momentum, of course, the momentum equation I did not explain to you. It is normally G beta delta T L cube divided by nu square is Grashof number. G beta delta T is only, the buoyancy force, and therefore G beta delta T is equal to Grashof number divided by Reynolds number square. Why? Because the viscosity square is found at the numerator for Grashof number, right? So therefore it is Grashof number by Reynolds number square. What is this ratio of kinematic viscosity to thermal diffusivity? If you look at the definition that I have given for Prandtl number, molecular momentum diffusion to thermal diffusion. It is a ratio of momentum diffusion to thermal diffusion. Prandtl number is equal to alpha by, nu by alpha. Okay, what is alpha? K by rho Cp. When I substitute K by rho Cp, you get it as mu Cp divided by K. So it's a Prandtl. Nusselt's number for a pipe flow heat transfer coefficient is given by the equation Nu suffix D is 4.36. Which one of the following combination of conditions does exactly apply for use of this equation? Okay, so what is it? Nusselt's D is equal to 4.36. It is for constant heat flux. Okay. Laminar flow, constant heat flux. Nu is equal to 3.66 for constant heat flux condition when it is laminar. Nu is equal to 4.36 for laminar and constant heat. For steady uniform flow through pipes, which constant heat flux applied to the wall? Which constant heat flux applied to the wall? What is the value of with constant heat flux applied to the wall? What is the value of Nusselt's number? It is 4.36. So 11 in all those fractions, The first one is close to 4 point something. So no one else is very close to that. Okay, therefore A. Okay. A fluid of thermal conductivity 1 watt per meter Kelvin flows in a fully developed flow with Reynolds number of 1500. 1500 means it is laminar through a pipe of diameter 10 centimeters. The heat transfer coefficient for a uniform heat flux, constant heat flux laminar, Nu is equal to 4.36. Okay. And uniform wall temperature, then Nu is equal to 3.66. So you calculate both of them. Straight away this. Nu is equal to Hd by K. You can calculate H in both the cases. Right? So here I am closing the convection heat transfer discussion. I will share all these presentations. I will share all these presentations to you. You can just go through these problems and get back to me. The only difficulty here is I am not in a position to directly interact with you. I am not in a position to directly interact with you. So all your doubts, unless otherwise you mail it to me, I cannot be in a position to understand where exactly you're finding difficult in listening to me. Right? So maybe it's only 5 minutes for me to start the heat exchangers. Now, I thought of explaining this condensation and boiling to you, but condensation boiling is not included in the GATE syllabus. So therefore, I am not going to discuss condensation and boiling. And if time permits towards the end, I briefly, for about 10-15 minutes, I can explain condensation and boiling. Tomorrow, we shall complete the theory and problems associated with both the heat exchangers, entire heat exchangers of parallel flow, counter flow, and other types of heat exchangers like cross flow heat exchangers and shell and tube heat exchangers. We'll do that. Okay. Thank you very much. I'm leaving you a little early today. So don't thank me for this. Thank you very much. All the very best to you.